Again, go back to the, not the last class before that. We had this explanation of the Newton's second law, which is basically the same thing we had in dynamics, but we are going to apply it to a control volume. So that's my CV, control volume. Right? And as you can see, the fluid, because it's control volume, the fluid is coming in and leaving out. Right? So we're going to apply Newton's second law to the control volume. And then we did it last class. I just want to reiterate over it. So here for MV, I need to put the mass of the entire control volume. How can I do that? Well, you use the differential form. Density is equal to mass per volume. And you know that you can write it dm over dv for infinitesimal element here, right? And then you would say the entire mass, so look at it, dm is equal to rho dv. And then you say the entire mass that are plugging into Newton's second law, this is for the entire mass in the control volume. You have what? Integral. So you're going to get the mass, you put it here, or m is equal to integral rho dv. And what type of integral is that? Integral? Is it surface integral, volume integral, line integral? What type of integral is it? You should say that very quickly. We have solved a lot of problems so far. What type?
Since it's a volume, wouldn't it be a triple integral?
That's right. That's exactly what I want to hear. So this one, although I put one integral here, but sometimes they put a v, that means over volume, or they put the triple, they don't put v anymore. Triple means volume, rho dv. Now, can you tell me something is wrong, that's still not wrong, is missing here in this sentence? Can you spot it? What's missing there? The ring is closed. You know that if I add these tiny elements inside this volume, I have to do it over full volume. That means if I start with 1 point and add them all together, I have to come back to 1 point just before it. So there is a circle here. Now let's plug in back into Newton's law. What do I get? I get the total derivative for m. I just write this, right? And then bring the v in. This is velocity, this is not volume. Bring the v in. So you're going to have the triple integral rho dv. That's for your m right here. And then times v, velocity. The total derivative of this is equal to what? The sum of all the forces on the control volume. And these are the external forces. The right hand side, these are the external forces that pass through the control volume. For example, if a fluid passes through walls, let's say there was a wall here, what forces do you get from the wall? The viscous friction force from the wall. Why? Because the fluid will attach to the wall. So these are the purely external. It has nothing to do with fluid. The external force, for example, if you have a blade and rotate it, that's your force coming from your hand. right? These are the external forms. All right, so these are external. So look at this equation. We have already done this before, so I just want to reiterate. So this guy is the total derivative. For total derivative, I'm talking about the rate of change of the masses within the volume plus minus the one that give out and come in. I have to include also the surface. We have done it before. So for the total derivative, we write the local derivative of this integral. Rho now you can bring the velocity in. V times dv, right? Plus the surface integral. Rho v times v dot m ds. So this entire thing is just the same thing we did before. You remember we converted the total derivative at a point. We had d dt was local t plus v dot m es. And this was a placeholder. That's exactly this. This is just the mass. You see this placeholder right now is this guy. And we had, before continuity, we had this form. I'm going to erase it. Rho dv. My placeholder was that for continuity. Surface integral. Rho v dot n es is equal to 0. This was what? The total change of mass is equal to 0. Conservation of mass. Conservation of mass. We had this before, this just a side, but I just want to show you the placeholder we put there empty was just rho for conservation of mass. And we got some total derivative of mass is equal to 0. Now the total derivative is not 0, it's equal to summation of external forces. But the placeholder, you see the placeholder is rho v. So compare that with this. Instead of rho, we have rho v. So the local derivative plus the surface derivative. Instead of here, this rho, we have rho v. And then v dot nds is equal to, this is equal to what? The derivative is equal to what? Look at it. Sum of the forces. This is called the most general form. The most general form of the momentum equations. Now my question for you, in two-dimensional, assuming your flow is two-dimensional, how many equations are these? You see, this is a vector. Say that?
2D?
In 2D, how many equations? In 2D, what's your velocity? Whose velocity? What is your velocity? You have u component and v component. So how many equations are these? Two. What about 3D? 3. Now in continuity, how many equations is that in 2D? Let me ask. This is not safe. Random number. How many equations are these in 2D? Look at the placeholder. What is that guy? Is it a?
It's rho, so wouldn't it just be one equation?
It's a scalar, one equation. Now, what's the word today? Okay. How many equations do I have for continuity in 3D?
3D? 2 equations?
Say that again?
2.
What is that like?
Rho.
So in 3D, how many, do you have rho in different directions? It's a scalar, right? So how many equations is that in each one? Just one. So continuity equation is only one equation, no matter what dimension you have. But the momentum, in 2D you have two equations, in 3D you have three equations. In 1D, how many equations you have? Momentum in 1D. 1D like a pipe, coming in, leaving out. You have only U. How many equations you have? One. But the continuity is always one equation. Alright? So this equation, let me show you what page number is that in your book. So you need to also read the book. That is equation number 619 in page. Equation number 619. And this page 315. 315 in the chapter number 6, momentum. Right? Now what I want to do, I want to also, I just mentioned that in 2D is what, in 3D is what. I also want to show you how this thing is written in 2D, 3D separately. Right? So in 2D, I'm going to write here. In 2 dimensions, we have in 2 dimensions, we have in 2D, we have. So here, I'll have one for U, one for V. Why? Because you want to write V is equal to UI plus EJ, right? I get one equation for U, one equation for V. So this is one equation for U, partial T, volume integral, rho U dV plus the surface integral, rho U, and then V dot N. This is just a scalar. It's a volume rate times ds is equal to some forces. Quiz waiver, something is missing here. Can you tell me?
The vector line over that. Some forces.
You're getting close to that. But it's not a vector line. It's something else.
Some of the forces in the x direction.
You said that? Okay, awesome. Quiz waiver here. Some force in the x. Why? Because this guy is only written in the x direction. Right? In vector statics, all the motions are zero. So you would have something zero. But when you have the dynamic, in the Lagrangian dynamic, you had that. This was dynamic. Now in the fluid mechanics, you have extra this guy that you have to deal with. Because it's coming in and leaving out. So it's level of sorry with that vector statics, then this was the dynamic. So you only had dD dt. And then you have convective, this called the is convective term. Convective terms. Why? Because it's just a guy that coming in and leaving out, you see, over the surface. That's the surface integral. Now, there was an x here, some x. Now what about y? Partial t, rho v. You see? The v component, the velocity component in the y direction. dv plus surface integral rho v times v dot n ds is equal to some force in y. And you can guess for the z component, if I have 3D, what should I do? Omega or w, the v component in the 3D, the w, the rest is steady. Some force in z direction. Alright? Now I want to go a little bit more than that and talk about, so the left hand side we're pretty much done for momentum. The right hand side, some of external forces. So what external forces do I have on the contour volume? Can you tell me in the real life?
Wait.
Gravity?
Gravity, yeah.
Yeah, the gravity is a body force, that's right. One thing is the gravity, right? So the gravity for each element, this is elemental, right? You have different elements, you have infinite elements here, right? So for each element, you have gravity. What is that gravity? Is the mass of this guy, what's the mass of this guy? dm, right? Times the g. Now g, because the gravity always goes down, define g, because this is a vector equation. Define g as a vector that goes down. So I put a row head on top of it. That means this guy is what? The magnitude of g times k negative. You see that? Negative g times k, it goes down. So for elegant formulation, define it like this. So when we plug in the formula, we don't end up with mistakes. Right? What else do I have? External force. Let's go over the surface of object. Imagine this fluid moving through the pipe.
Friction?
The friction, so there's going to be some shear stress. If it goes this way, the shear stress tau is always this way. And it's very complicated. We talk about this later, not today. Right? What else do I have? Let's say, you see this truck is moving. And behind the truck, you have this circulation and then pressure drop. So there is a pressure force. Right? You see that? We feel that when you move an object, there is a pressure difference. So there are pressure forces. What is the direction of pressure force? If this is normal, these are normal, right? These are normal. The direction of pressure is what? Opposite to the normal, and it's always 90 degrees. This force comes from pressure. And what is that? It's just P dot times dA. That's dF. Right? And it's a vector, it's not as P dot dA. You have P dot dA in the x direction, P dot dA in the y direction, P dot dA. So the way you write it is like this. dF, the infinitesimal force comes from that, is equal to negative P dot times N dA or ds. In this case, we said the surface, you remember our definition, we took this dA is equal to ds. We just use a different symbol. Instead of A, we said S. So A was just the total area, ds was infinitesimal area of that element. So the pressure force is what? You see it's a vector in x, y, z, so there is a arrow head here. And then P is a scalar, but look, we are multiplying by normal vector, opposite to that. So if the normal vector is going there, opposite is this way. So P dot N, not dot, P N, yes, so it's going this way. So that's your, actually dF. The force comes from the pressure only, right? So general, let's write this as a mathematical expression. So that's what I'm doing here. For external force, for external forces, we can write some forces external for the right hand side of the momentum equation is equal to forces due to friction or tau plus forces due to pressure plus forces due to gravity. Right? So for that, I know that for this guy was dF is equal to P N ds negative. This guy was dF is equal to dm times g, well, it's a vector, and this one unit vector. And this guy, I want to talk about it, we'll talk about this later. Because if I talk about it right now, first of all, we don't have time. This is it's called tensor. So in 3D, it has different direction. It's more general than vector. Secondly, if I talk it right now, the course is finished. So we have next chapter and next chapter and next chapter to talk about this side later. Right? We'll talk later. Now, what if we assume there is no friction right now? Let's say the frictional forces are very small. This is actually a practical, it's not just mathematical construct. We want to make our life easier. No. In the real life, there are a lot of flows in a physical problem that the friction contribution is very small. So if this is, for example, 1,000 Newton, this guy is like 200 Newton, this is 0.1 Newton. So even if you compute it and contribute it, it's just so small. So in this case, yes.
In the lab, we were, or I was reading one of the handouts, and it mentioned that in certain cases, you completely ignore gravity as well.
Yeah. When can you ignore the gravity? Can you tell me?
In the back.
Huh?
When everything's horizontal.
Exactly. Quiz waiver. Even quiz waiver. When the thing is horizontal, you have, well, gravity, but the delta, I'm going to reach to that hopefully today, I'm going to reach to the Bernoulli equation. We had this lab coming last week, so I postponed it to today, so we match the theory with the lab, hopefully. But there is a part of the lab that is from the last chapter in the course that we can never match, unless we just do the lab next semester. There is no way to match it up. So that's the reason I postponed it. Hopefully I'll be able to cover that theory, and then we can go to that again. All right, so when you have your test bed flat, there is a gravity force, but the delta Z is the term that will show up hopefully soon. That delta Z is 0. So although you have gravity, the delta Z is 0, and then this term also is 0. All right? So right now, let's say after this point in this class, we assume the flow is frictionless. So we call it inviscid flow, or you can put it this way, ignore or neglect the friction, aka shear stress. Now if I ignore that, this term is just, I'll make it 0. Right? For right now. Later on, we come back to the same equation. So this is the most glorious form. We come back to this form and say, now let's add the friction. So you see extra term in the equation. So right now, let's ignore that friction. So what do we get? I'm going to write it here. In that case, the external force, some force external, becomes what? Negative P N Vs, right? For element, plus Vm, instead of Vm, you can write what? Rho dV. Instead of Vm, you write rho dV, right? Then you write what? Rho G dV. So this rho dV is dm times G. You see that? Now guys, pay attention. This is for what? The forces in one tiny element, one of these guys. Right? This is just on one of these guys. I wrote that some of external force group. That's for what? Control volume. The entire control volume. So what am I missing here? What should I add? Integral. So this is what? What type of integral is that? Triple or double? This is the pressure. The fixed pressure acts only on the face, right? So this is a double and close. All faces. Close that volume. What about this guy? What type of integral is it? So let's put it together. So I just write this equation using final form. All right. Partial t. It's just the same left-hand side. Volume integral rho v dv over this volume plus the surface integral rho v times v dot n ds. Right? But instead of external forces, some F are used this equation, this external force. So what I'm going to do, I'm going to write is equal to the surface integral negative P n ds over the surface plus volume integral rho g dv. That's it. This inviscid momentum equation. And because a guy named Leonard Euler drew this the first time, he drew it in 1700. How many years ago? 300 years ago. They call this AKA Euler equation. Euler equation. And in fact, the fluid mechanics is the Euler science, Euler equation. But because the two guys, one guy was Navier and the other one is Stokes. These two guys, they figured out the viscosity. So this is the shear stress viscosity, this is complicated math. And they added to that, so you have extra 10 coming here from viscosity. Then they call this Navier-Stokes equation. But in fact, it's Euler equation, frictionless Euler. When you have friction, this is the inviscid. When you have viscosity or friction, it's called Navier-Stokes. It's just different vocabulary. You get a little bit confused when you start the first time, but later on, everything's going to be straight. Now, what I want to do, I want to find the differential form, because that's the one that I use to drive Bernoulli equation. If I can drive, I'm going to give a homework to you. Start from here for the control volume and drive Bernoulli equation. But right now I want to get differential form, and then from differential form I want to drive Bernoulli equation. So how can I drive the differential form, which is chapter 7? The author dedicated one entire chapter for that, chapter 7, but we can just get it right here. From the divergence theorem. So you have integral over face Q and ds is equal to volume integral divergence Q dv. This is the divergence theorem. Look, let's apply divergence theorem, but only to this term. Apply the divergence. And also this term, y. Apply the.
To make it all triple integrals,
Yeah, why should I make all triple integral?
those are easier to solve.
Because I can factor out the integral and then say inside the integral is 0. Okay, when you take integral over any volume, if it's 0, what do you mean? Inside the integral must be 0. If your integral is arbitrary over arbitrary volume. So what do I get if I apply divergence theorem to that? Look, that's your Q. Right? This is your Q. Pay attention. This guy is your placeholder. This is like a placeholder Q. Right? If this is Q, the divergence form of that is going to be volume integral divergence of whatever you have, the Q. Look, the divergence of Q. So the divergence of, what's my Q? Rho, V, and another V. Right? D, V, over volume. What about divergence form for this guy? What's your Q here? The Q is this guy. So you get volume integral, right? Take the negative sign out, so you put it here, and then divergence P dV. That's it. Now, put them all together, so that's what I'm going to do here. Factor 1 integral. So if you put these together, you get this. Volume integral and factor it out. And then inside that, we get rho d dt, rho v, plus divergence rho v times v is equal to, and take also the y to the left, negative, gradient p times, and then this guy also, take it, this becomes positive, negative, rho g, right? dv. So what did I do? I plugged these two inside that, right? And then I took everything to the left side, and then I factor out the triple integral. So you get triple integral of the time derivative rho v plus the divergence of rho vv, right, the convective term. And then you see this is negative. When you take it to the left-hand side, what do you get for pressure? Positive. Negative, you take it to the left-hand side, positive. Gradient P. Right? And then what else? Rho g is positive here. When you take it left, what do you get? Negative rho g. Easy. The entire thing times dv. This is nothing new except combining all EQs, all the equations. You get that? So if the volume integral of something is 0, what can I tell about this guy? It's a volume integral over arbitrary volume, not just a specific volume. You may be able to choose a volume such that you get symmetry, so it cancels out. But for any volume, if the volume integral is 0, what can you tell about this guy? Let me ask Emily, what can you tell about this guy?
What is the question again?
If the volume integral is 0, what can I tell about the integrand? Go back to calculus. If you have integral f is equal to 0 from a to b, right? And a and b is arbitrary, so you have this your f, right, versus x. So any integral you pick, if the integral is 0, what can you tell about f? What is it about f?
0.
Equal to 0. Is equal to 0. You know, I can, instead of doing this, which is the right way, it's probably going to take you a steep learning curve, but after you get that, you totally understand. I could give you the formula, like this is for pressure drop, this is for, and you memorize it like technician style kind of learning, but that's not the way engineer learn. Engineer learns from the first principle. It's called first principle. We start with Newton laws, and then we drive this. You really need to practice that. That means you need to go back to calculus and review all these things. You already put an announcement beginning of semester. I said, please review calculus. Right? So, if I get that 0, I get the differential. The original form, this is called the control volume or the integral form. It's called control volume. Or integral form. But this guy, I know this is 0, so you get this right here. Partial derivative rho v plus divergence rho v plus gradient p minus rho g is equal to 0. This guy must be 0, right? This one is the equation. They call this the differential form. Chapter 7. In fact, these two are exactly the same thing. They are exactly the same thing. But this guy is written for that big potato, the control volume. This guy is written at any point for that tiny infinitesimal element. Now, how many equations, go back to, how many equations are these in 2D? How many equations in 2D? 2. What about 3D? 3. Why? Well, look, rho is just a scalar, but rho v is a quantity that has direction, you see, because v has a direction. It's in the x is rho u, in the y is rho v, in the z is rho w. So let me write the differential form for 3 different directions. Just like I did for 1 and 4, and then you get close. See that to the end. So if you plug for v with u, you get in the x direction. X direction, you get what? Partial derivative of time rho u plus divergence of rho u, but this guy, look, d dot n is just look volume gradient. So this guy is just by itself is scalar. Plus, there is no n here. D dot n. Let's call it q. Plus partial p, partial x. The gradient of pressure is what in the x direction? Partial p, partial x. What about in the y direction? Partial p, partial y. Minus rho g x. Rho times the component of gravity in x. Now if I take my coordinate system, the regular, so y goes up. What's my gx, the component of gravity in the x direction? 0. But I try to make the general form. So later on, if you rotate your coordinate system like inclined problem, then you get this component, g sin theta, is equal to 0. What about y component? So before I do that, I want to expand that. The divergence is what? So that's right here, partial u, partial t, plus this is partial x, rho u plus partial y, rho v, rho u v plus partial z, rho u w. That's what you get from this step. Plus partial p partial x is equal to rho gx. So that's the momentum in the x direction. What about y direction? You plug v here for velocity, you plug v, the lowercase v. So you get partial t, rho v, plus here you get partial x, rho v times u, plus partial y, rho v times v, plus partial z, rho v times w, plus the gradient in the y is equal to rho g y. And in the z direction, this is y here. And in the z here, you get partial t rho w plus partial x rho w u plus partial y rho, I'm messing up this one, rho w rho w v plus partial z rho w plus the gradient z is equal to rho g z. Three equations. We visit momentum equation in 3 cases. So this guy, you see, this is the beauty of vector form, because this guy is like you zip this data like a zip file. You put it in a zip file, it's just one line. All right, so I want to drive Bernoulli equation from that. So let's do this. Consider the differential form and integrate between 2 points on the streamline. So let's say, I just wrote here, integrate the differential form. So let's say this is streamline. V comes here, got it, V at 1, pressure at 1, density at midpoint, and let's say also incompressible. We have compressible form for Bernoulli, but we don't do it in this course. We just do incompressible, right? So you have V at this point 1, at this point in this flow. This is a streamline. So you can consider like a pipe. It's a pipe, and you have a streamline inside a pipe. You have velocity here, pressure here, density here, and the height. Let's say between these 2 points. Let's say this point here. So you can show the height difference. This point 2, right? And between these 2 points, you have that height difference. There you go. Call this h. And then the velocity, when it comes here, the particle gets v2, p2, and then the density is same. Density constant with the same density. So let's integrate this equation over the streamline. So my element here, when I integrate, my element is, this is dr, r vector. My element is going to be dr. And I want to do the line integral of both sides of this. That's right here. The line integral from point 1 to point 2, whatever here my momentum equation is, right? Momentum dr, so you have dot dr, is equal to what? The right hand side, the line integral 0 is what? 0. So you plug in momentum and take the line integral. But before I do that, I want to actually apply continuity to that to make it simpler than that. So this equation, let's apply continuity to that. So what are the equations of continuity? You have 2 form, one integral, one differential. We already covered that. So the differential form for continuity, I'm going to write here. So the continuity equation, you have what? Partial rho, partial t, plus divergence rho v is equal to 0. This is differential form, we already had it before. Form of continuity equation. Right? So I want to apply this guy, because this is a different equation. This equation is different from here. I want to apply that to this equation. So let's expand this equation. So if you expand the equation, this term will give you partial rho, partial t, times v, plus rho dv proportional dt plus this one is going to give you divergence rho v times v plus rho v divergence v gradient v plus this term is going to be the same gradient v plus this term is just the same. So you have negative rho g. Right? Is equal to 0. Guys, look at it. Here, this guy and this guy. Let's write it this way. Partial rho, partial t, plus divergence rho v. The entire thing times v. Can I write it this way? Just factor out velocity. V times that, V times this, right? Plus, the rest is rho, derivative of that with respect to time, plus rho v, gradient v, plus gradient v minus rho g is equal to 0. What is that? What is this there? Can you tell me? Look at the whiteboard. What is this there?
Divergence theorem?
No.
No, sorry.
What is this there? Just look at the whiteboard. It must be there.
Differential continuity.
Huh?
Differential continuity.
Which is? We don't have time for that. Look, this guy isn't that the same thing?
Yeah, so it's just 0.
It's just 0. It's going to 0.
Okay.
So you get what? You get this alternative form of momentum equation. And this one is the one that I use the Bernoulli, to write the Bernoulli that you get.
I was gonna ask if that's how it works for every single situation.
Yeah.
Okay.
Except you have, when you have, this is general, you have to have this implicit, no viscosity. But later on, next chapter, hopefully by that time we have reviewed the calculus and everything. Then when I draw the stress tensor, we put it here, then you have extra term come from viscosity. And then you have full Navier-Stokes equation. This is a Navier-Stokes equation without the stress. Now, this equation I integrated over the streamline. First of all, the streamline, let's assume it's just constant. There is no time derivative. Then I get rid of this term. I get rid of this term, there is no time derivative. So what do I have? So you say, here for momentum, you just want to put what? Rho v gradient v minus plus gradient pressure minus rho v, right? For momentum. So this one dot dr is equal to 0. Integral from point 1 to point 2. So let's do the integral. What do I get from that? This guy, you take the rho out, integral v gradient v dot dr from point 1 to point 2. And this is rho. You take it out. Why do I take the rho density out? Incompressible. It's incompressible. You take rho out. Plus the next one. Integral from point 1 to point 2 of the gradient of pressure. Integral point 1 to point 2, gradient of pressure, plus integral point 1 to point 2 of rho, take the rho out, times g. This is dot dr, and this is dot dr. Dot dr. This must be equal to 0. What can I say about this guy? When you have integral u du, what do you get? Yeah, you get u2 over 2. But this is a vector form. V dot grad v dot dr. This is a vector form. So this guy, you get magnitude of v. I'm going to write here magnitude of v. The square over 2. Just like this. From point 1 to 2. Plus the next one. What do I get for that? Gradient pressure dr, from this point to this point. You remember the calculus, we had exact differential? When you had exact differential, what would you write for integral? The integral is path independent. These are all exactly differential. The integral is path dependent. So what do you get? If you get, when you find this, for example, from point 1 to 2, what do you get? Just cancel out this 2. You have dp, right? What do you get from this integral? Integral dp from 1 to 2. What do you get? Say that? Say that? P2 minus P1. P2 minus P1. That's exactly what this. So this is going to be P2 minus P1. And this guy you already, so I'm going to write here plus delta P from point 1 to 2. And the last guy, you have negative rho g. What's a path integral from rho g from point 1 to 2? You do g dot dr. G is this way always, you see? And dr this way. So when you do dot product, what do we get from 1 to 2? You got just the h, right? G dot h. No x, no y, no z, just the h. So that's going to be rho g h from 1 to 2 is equal to 0. This is called Bernoulli equation. It's just, if somebody asks you Bernoulli equation, well, you say it's just my momentum equation, but I just already integrated over a cylinder. So next class, so it's called Bernoulli over M equation. Next class, we are going to use this in practical problem, which we are going to do it today in the lab. Unfortunately, there is no way to synchronize lab with the theory, but we are working on that. Let's go.